we're going to talk about a new mathematical topic for you and me. It's called systems of linear equations. Now, of course, we've been dealing with linear equations already, so this isn't completely new, but the idea of a system of linear equations is new for us. These kinds of problems are going to arise very naturally because they basically deal with trying to find when two lines intersect. And knowing when two lines intersect has lots of applications. So what in the world is a system of linear equations? Well, it's actually basic, and it is this. A set of two or more linear equations form a system of linear equations. In some ways, we want to think of the equations as linked together. And we say that an ordered pair that makes all of the equations in the system true is a solution of the system. So let's take a quick example and just make sure we understand this idea of a solution of a system. Here's a very small system of linear equations. Y equals 2x minus 5 and y equals x minus 2. Those two equations taken as a little group forms a system of linear equations. A solution of this system is x equals 3 and y equals 1, or written as an ordered pair, simply 3, 1. Let's quickly confirm that 3, 1 really is a solution of this system. In the first equation, we substitute x equals 3, y equals 1, and we get 1 equals 2 times 3 minus 5, or 1 equals 6 minus 5, or 1 equals 1. And of course, that's a true statement. Now, we're not done, though, checking that this is a solution of the system. We have to make sure that this point is a solution for every one of the equations. So now I have to go to the second equation and make a very similar substitution. I want to let x equals 3 and y equal 1. And I will have 1 equals 3 minus 2, or 1 equals 1. And that's true as well. What does that mean? I've now shown you a solution for both equations in the system. And therefore, I say that 3, 1 is a solution of the whole system. Well, I'll try to show you at least one word problem by the end of this lesson. But for now, the biggest question we should ask is this. If we're given a system of just two linear equations, how would we find the solution? See, what I just did with you, I actually gave you the solution, and we just checked to make sure it was a solution. I'd like to now know how we find the solution if the only thing we're given is the set of linear equations. By the way, before we go anywhere, systems of linear equations can be bigger than just two equations. You could have 3 equations or 4 equations. We're just going to focus on systems of 2 linear equations here in this lesson. Now, in this lesson, I'm going to show you 2 specialized techniques for solving systems of linear equations. They're called solving by graphing and solving by substitution. And I want to start with solving by graphing. You can probably imagine that graphs are going to come into play here. So here's a question. From a graphing perspective, what does a solution of the system y equals 2x minus 5 and y equals x minus 2 look like? I mean, what does it mean to be a solution if you're thinking about it in the context of the graphs? Well, such a solution needs to be a point on each of the 2 lines, and it needs to be the same point on both lines. How can that happen? It happens if the point is an intersection point, a point where the 2 lines cross. So let's solve this same system by graphing that I looked at earlier. The technique is actually pretty straightforward. You start by just graphing the 2 lines that you were given and finding the intersection point. So I've graphed the 2 lines for you in this figure, and now I see that the 2 lines actually do cross one another. Now, of course, we had to make sure we knew how to draw the 2 lines, but we've done that in previous lessons. So I've drawn them here for you, and now I want you to notice where the intersection point is located. The point where these 2 lines cross is exactly 3, 1. And of course, the y-intercepts are -2 and -5. But I see from the sketch of this graph, or I should say the sketch of these 2 graphs, that the intersection point is 3, if I draw the graph carefully on some graph paper, I can sometimes find that intersection point really accurately. And in this case, that's exactly what we did. Now, before we move on to the next example, let me make another comment. Notice something like graph paper is really like a must here. You could draw these graphs somewhat sloppily on a piece of blank paper, but if you really had to find that 3, 1, you'd have to really draw carefully. And what if you saw the intersection point, but you said it was 2, 1, or you said it was 3, 0.9 or something like that? That's not going to cut it. You've got to have more accuracy than that. So this graph paper isn't just a helpful thing. It's really a must in these examples. And let me also point out that it would probably be very smart to check your solutions after you've done them by graphing by plugging in the information into the equations just to make sure you got everything right. I think that would be very, very wise. Now, with that said, I'd like to move to another example, and I want to solve this system that I'm about to give you by graphing. So we're going to use our graph paper, and we're going to solve the system that way. The system is going to be y equals negative 2x plus 3 and y equals 3x minus 7. So before I draw the graphs, notice that we're guaranteed to find a solution based on the equations we were given. Now you might say to me, how in the world do you know that? Well, look at the slopes for just a second of the 2 lines that I gave you. One of the slopes is negative, and the other slope is positive. So if you just think about what the graphs are going to have to look like in general, one of the lines is going to have to go like this, and the other line is going to have to come up like this because the slopes have different signs. Well, the 2 lines will have to cross somewhere then. There's no way they can be parallel because one of them is going to be going up like this, and the other one is going to be going down like this. So I don't know where that crossing point is going to be yet, and I certainly don't know at the angle at which the lines are going to cross one another, but I don't care about that. All I care about is where is that intersection point. And now I say we can actually find it. So what we want to do is draw the graphs of the 2 lines in question. And when you do that, you notice that both lines are in slope-intercept form, so you know where the intercepts of both lines are, and you can figure out another point on each line using the slope, and then you can just connect the dots to find your 2 lines. As soon as you've done that, you look for the intersection point between the 2 straight lines you've just drawn. And again, if you're fortunate, you'll be able to see what that point of intersection is. In this case, the numbers work out very well, and the solution appears to be at x equals 2 and y equals negative 1, down in the 4th quadrant. So I claim that my solution is 2, negative 1. Now, as I said a few minutes ago, I think it would be wise to actually check that that's the solution, now that we think that's what it is, by plugging in x equals 2 and y equals negative 1 into each of the 2 equations that we started with. So let's do that here. The first equation was y equals negative 2x plus 3. I'm going to plug in x equals 2 and y equals negative 1, and here's what I'll get. Negative 1 equals negative 2 times 2 plus 3. That's saying the same thing as negative 1 equals negative 4 plus 3, and negative 4 plus 3 is negative 1. So I have the statement, negative 1 is negative 1. And of course that's true. Great. I'm not done though until I plug in the same information to the other equation and make sure I get a true statement there. So in that case, I'm going to plug in 2, negative 1 into the equation y equals 3x minus 7. And when I do that, I'm going to have negative 1 equals 3 times 2 minus 7. That's the same as negative 1 equals 6 minus 7, which is also negative 1 equals negative 1. So, indeed, 2, negative 1 really gives the